Hello again. In this video, we will discuss some notation pertinent to Chapter 1. Vectors, recall, have three bits of notation: symbolic, geometric, as arrows, or as ordered lists of real numbers. Points are denoted with letters in front, often P and Q, then followed by, in parentheses, the coordinates of those points. It should be clear that points are simple dots. Vectors are arrows. A notion that's important is called the norm, or the length of a vector, also called the magnitude. It's a very simple quantity, and it's computed like this. For a vector with coordinates v1 and v2, the norm of that vector has this symbol, and it's simply v1 squared plus v2 squared, and then the square root of all of that. So it's just basically the square root of the sum of the squares. You'll notice the similarities of this formula with the distance formula. Indeed, it's related because the norm gives you the distance between the tip of the vector to the origin, the 0, 0 vector. The unit vector has length equal to 1. You can always create a unit vector by starting with a vector and then dividing it, really scaling it by 1 over its norm. So you think of rescaling the vector by a factor of 1 over its length. It has the result that the new vector has length 1. There are some standard unit vectors. We denote them with I, J, and sometimes K, depending on what dimension we're in. They're simply these familiar vectors. They're simply the vectors 1, 0, 0, 1, or in R3, 1, 0, 0, 0, 1, 0, 0, 0, 1. The distance between vectors will be computed like this. Again, recognize how similar this is to the standard notion of distance you might have seen before. For vectors u and v, given by coordinates u1, u2, u3, v has components v1, v2, v3. The distance between those two vectors is given by the square of the difference in their first coordinate added to the square of the difference in the second coordinates added to the square of the difference of the third coordinates and the square root of all of that. This is simply the distance formula. Now the dot product of two vectors is a new idea. The dot product goes like this. Given vectors u and v, expressed in terms of their components, we take the dot product we symbolize the dot product with a simple dot between the two vectors, and we compute it like so. We take the first coordinate of u and the first coordinate of v, multiply them together using normal multiplication of real numbers, and then add that to what we get when we multiply the second coordinates together, and then add that to what we get when we multiply the third coordinates together. So u3 times v3. So we have this sum of the products of the coordinates giving us the dot product. This is a very useful quantity. In particular, it gives us it helps us to compute the angle between the vectors in R2 or R3. In those low dimensional spaces, the angle between the two vectors is computed as follows. So you take the dot product of u and v divided by the norm, the products of the norms of the two vectors, and then the inverse cosine of that gives us the angle between the two vectors. We will discuss where these formulas come from in future, but for now just know that this is a simple consequence of the law of cosines. Section 1.2. We begin with this theorem that says for any vector in Rn and any scalar, so any real number, the following three properties hold. The norm of that vector is always non-negative. It's either 0 or positive, and it's 0 if and only if it's a 0 vector. And in part C, notice that the norm of a scaled vector is equivalent to the absolute value of the scalar multiplied by the norm of the vector. So in a sense, the scalar comes out, but it comes out as an absolute value. And it's this formula that gives us the unit vector that we saw earlier. For an example, for the simple standard unit vector 1, 0, its norm would be 1, whereas the norm of the vector -3 times this 1, 0 vector is equal to 3 times that norm, which is 3. And so indeed, this scalar does come out as an absolute value. So every vector can be expressed as a linear combination of standard unit vectors. Let's see an example of that. So here's a randomly chosen vector, -2, 5, 7. It's expressed as a linear combination of the vector I and the vector j and the vector k, where 7, 5, and -2 are the coefficients of the linear combination. So in particular, we take notice you get -2 times 1, then we have to add that to 5 times 0, that gives us nothing. Add that to 7 times 0, that gives us nothing. So the only contribution to this first coordinate comes from the I vector. Likewise, the only contribution to the 5 comes from the j vector, and the k vector returns 7 in the third component. Moving on to another important theorem in section 1.2, and we can paraphrase it like so. The distance in Rn, as we've defined it, conforms to all of our expected notions of distance. It's always non-negative, it's only equal to 0 when the two vectors are equal, and it's symmetric. So the distance from A to B is the same as the distance from B to A. If U and V are equal, then the dot product of U and V is the same as the dot product of U with itself, which has this formula, which is the square of the norm formula. So the square of the norm formula gives us basically the square of the distance, the square of the length of a vector U, and that's equal to the dot product of a vector with itself. So if theta is obtuse, then we have an obtuse angle, and the cosine of that will be negative. Connecting it with this formula means our dot product will be negative. So our dot product, again, the sign of it tells us something of the angle. It tells us in particular that if the dot product is negative, then the angle between the two vectors is obtuse, and the dot product is positive, then the angle between the two vectors is acute. We'll see that if the dot product is 0, then the angle between the two vectors is 90 degrees. Now let's look at some more algebraic properties of the dot product. It is symmetric. U dot V is equal to V dot U. You want to look in the textbook for justification why, but for now, let's move on to part B. It is distributive. U dot, the sum of V plus W, is the same as U dot V plus U dot W. Page 19 has several more important properties, and you want to read all of those there, noting along the way that this theorem really contains the foundation for all of Euclidean geometry, so it's worth taking a look at. Here's some examples. Let's take the vector 1, 2, 3 and dot it with the vector 3, 7, and 2. Well, what do? We take 1 times 3 plus 2 times 7 plus 3 times 2, and we get 23. Now if we swap these around and first dot 3, 7, 2 with the vector 1, 2, 3, we obviously get the same thing, basically because real multiplication is symmetric. So 1 times 3 is the same thing as 3 times 1. So this is an example of the dot product being symmetric. Theorem 1.2.7 says that the dot product of the zero vector with any vector is 0. And in particular, it's the zero scalar. In more detail, if we take 0, 0, dot 1, 2, 0 times 1 plus 0 times 2 is 0. The distributive property, like we mentioned before, for the distributive property, let's take this example. If we take the sum of two vectors and then dot it with the vector 5, 6, well, we'll get 56. On the other hand, if we take 1, 2 and dot it with 5, 6, and then take the vector 3, 4 and dot it with the vector 5, 6, guess what? We also get 56. So this tells us that this formula holds in this case, and this is just a simple example of this more general formula. Page 20 has several more examples. You want to read those carefully. Another important concept is the idea of orthogonality, which is really a fancy word for being perpendicular. Two vectors are orthogonal if their dot product is 0. So you want to think 90 degrees, you want to think perpendicular whenever the dot product is 0. And a set of vectors whose members are pairwise orthogonal, well, that's called an orthogonal set. These vectors look like they're orthogonal, they look perpendicular. The dot product of them should be 0, and indeed it is. 0 times 1 plus 1 times 0 is 0. These guys don't really look perpendicular, and so let's check their dot product. Negative 1 times 1 is negative 1, plus 1 times 0 is still negative 1. So these are not orthogonal, and we get a dot product that's not 0. So the 0 vector is orthogonal to everything because the 0 vector dotted with any vector gives us 0. That's the definition of what orthogonal means. But it's also parallel to every vector as well. Next, we have the idea of a set of orthonormal vectors. Ortho means the set's going to be orthogonal to each other, and normal means it's going to have length equal to 1. This comes from the idea that the process of making a vector have unit length is called normalizing. So the standard unit vectors are an orthonormal set, and this vector that these two vectors that I've drawn here, v and u, these are also orthonormal, as are the vector w and w prime. These two vectors are orthonormal. Finally, the Cauchy-Schwarz inequality says this: for any vectors u and v in Rn, the absolute value of the dot product is less than or equal to the product of the norms of the vectors. Now this simple stated formula is used to prove the triangle inequality, which we use quite a lot, which says that the norm of sum of two vectors is less than or equal to the sum of the norms. These examples below show that the three different instances of the triangle inequality. Notice we have equality when the two vectors are the same. If two vectors are orthogonal, we have the norm of the sum vector being strictly smaller than the sum of the norms. And if we have one of the vectors being the opposite of the other vector, well, then the norm of their sum is 0, which again is obviously smaller than the sum of their norms. That's all for today.